Hello everyone, welcome back to the Game Engine Development Workshop series. So before we get into our topic for today, which is hitboxes, I thought I'd show you something I'm currently working on. This is our scripting language that we'll be doing. It's not completely done, but it's mostly there. All I really have left to do is just sort of like integrate it fully with the engine. But I just thought I'd show you. So I have in my main file here just the simple thing. I'm creating an engine instance as we have been. Um, and then I just create a simple script and I run that. So right now this is doing test.script, which if we look at it is kind of weird. I was just doing some benchmarking on that. But change it to do this fib_r script. So this is a classic recursive Fibonacci number generator where you give it the index of the Fibonacci number you want, and it will sort of recursively call itself to get you the value you need. So classically very slow, but also a neat thing to do. So if this sort of style isn't familiar to you, this is basically an assembly language. Under the hood, it is all, obviously it's all like abstracted on top of a layer of C++, so it's much, much slower than an assembly language. In my benchmarking stuff, it seems to be about 1/10 the speed of native C++ code, simply because C++ was like actually running directly on the hardware, but also the compiler performs a lot of optimizations, and I don't have that kind of knowledge at all, so I haven't done anything that crazy. But it is designed, and we'll see more of this as we get into it. It is designed to be able to like fit into 64-bit words. I'm not actually doing that for this because there's not really a reason to, and it just added a lot of time to the development that was unnecessary. But I think when I actually end up using this myself in my own engine, the one I currently have is everything fits in 32-bit words, but that's a bit too restrictive. So this is designed to fit in 64-bit words. So if you're interested in that, you can like actually serialize this stuff and save the compiled files out to like your game file or whatever, so that when you load your game, you don't have to compile all your scripts. But anyways, I'll just run this. See, brings up the window here just because we are creating an engine instance there in our main file here, and then we're not doing anything with it in this script. So right now, it starts generating from 40. So it starts at index 40, so it's going to take a long time to get that first one. So there's 40, and then it'll sort of get faster and faster as we go down the chain here. Obviously, these numbers right now are too big to check, but we can validate by hand. These first couple, 0, 1, 1, 2, 3, 5, 8, 13. Yeah, so it does work. And I just did a mem dump here so we can see all the different registers, the stack, the memory. So yeah, that's just a bit of a preview. Hopefully you're looking forward to that. I think it's very cool. And the possibilities there are pretty extensive as well. Like you could actually write a higher level like C style language on top of this that then compiles down to that assembly that is then ultimately assembled into machine code if you do decide to go with the like actually fitting everything into 64-bit words and like designing a virtual CPU type thing. But yeah, anyways, so today's agenda, we're starting on hitboxes today. We finished all of our dynamic stuff last time. So first we're going to go over some like basic theory for rectangle intersection, and more importantly, like the scope of our specific problem, what we need to solve, because it turns out our case is a very specific kind of rectangle intersection that is quite easy. Then we'll just do some general housekeeping, just add a few methods here and there to make our life easier, just writing some of this code. Then we'll do like a simple hacky example in our main file, just to prove that like the theory we went over here actually works. And then we will go into theory for our global solution. And then hopefully by the end of today, we'll start working on our global solution. So I'm not going to really tell you what that means, but yeah, so let's just get into a bit of basic theory here. So I'll open up Paint. So it turns out that collision detection, and more so resolution, is an especially difficult problem. Classically so. In games, like, that is probably the number one bug in every game. Every game has it, where you can just clip through some wall, like, and people speed run with that. Um, there's just no way around it. Like, at a certain point, um, it's a very, very difficult problem. But we're only doing 2D stuff, which does simplify it math-wise for sure. But even within just 2D stuff, like, it's still kind of difficult, especially if you have like arbitrary geometry, like weird like polygons, especially if they're concave. Like, that's, I don't even know how to do that. Um, but yeah, so for more, if you're interested in that, for more complex 2D geometry, the algorithm that's generally used, I think, is called SAT, Separated Axis Theorem. I've never used it. It seems pretty simple, but it is like linear algebra heavy. So like understanding it might be a problem, but if you don't care about that, you can probably just like plug it in and use it. But I do believe that only works on convex shapes, even then. But anyways, we're not even interested in all that. We have an even simpler case, which is just rectangles. And furthermore, axis-aligned rectangles, meaning that our rectangles are always, like this. They're always sort of, their edges are parallel and perpendicular to each other. We're never going to have one that's like at some weird angle. Um, and this allows us to use what I believe is the simplest form of collision prevention, which is axis-aligned bounding boxes. Axis aligned meaning the rectangles are not rotated relative to each other, and bounding box just meaning that you can use like these corner points essentially, because they're just rectangles. It's very easy to calculate these to check for intersection. And this is, it's, I kind of refer to it as like the selection sort of collision resolution algorithms. As I was saying, like, for more complex geometry, you need a lot of linear algebra stuff. But this, like, um, it's kind of like something you come up with yourself. Like, I remember when I was first doing like game testing stuff in JavaScript, I don't know, like 6 years ago. I needed a simple system to just prevent collision resolution, and I came up with something sort of resembling AABB, axis aligned bounding boxes. It wasn't perfect, obviously, and it's, even though it is a simple algorithm, it's hard to get perfect. Um, but yeah, it's probably similar to you. Like, if you were, writing some code and you say, "Oh, I need this to be sorted. I don't want to just use a library function. I'll figure out how to sort it myself." You probably came up with something similar to selection sort or insertion sort, just like a slow n-squared algorithm that is sort of easy to figure out logically from nothing. So yeah, this is like the simplest case. But it turns out it works perfectly for our situation. We don't need anything more complex, which is great. So the real complexity of this section, handling collisions, is not in the math, which is nice because I am not as proficient in linear algebra as I would like to be. Okay, so instead of just jumping in and looking at collisions between two rectangles right away, let's look at collisions between a rectangle and a ray. So a ray just meaning like a vector, essentially, that has some origin in space and then extends in a direction in space to infinity. So we can look at the three like most extreme cases of two the most extreme, and then one like the most average case of intersection between a ray and a rectangle. So let's say I have a ray here. It just goes like straight through the middle of my rectangle there. And then I have another ray here that goes like straight through there. And this, obviously I've drawn it quite far away, but you can imagine that this is like infinitely close to the corner, and all of this will still hold true. And I have one here at the top corner as well. So obviously, to the eye, all three of these intersect with this rectangle. And now I can do a couple that don't intersect, drawn in blue. And again, clearly these do not intersect. So what's the difference between these two? Well, the reason I drew these like black sort of extensions of our rectangle's faces here is so that we can visualize some like the relationship between these faces and our rays here. So I'll sort of just extend these out till they hit all of these. And then we can look at the points. So this plane right here, or well, I guess it's not a plane, this line will be our near y plane. This will be our far y plane. And similarly, this will be our near x. And this will be our far x. Okay. So we can now calculate some points. So for this vector here, this point is the near y, the point at which it intersects with this near y line. This point right here on the face is the near x. This point right here is the far y. And then all the way down here is the far x. So we'll go ahead and just label that for all of these vectors here. In this case, because we're going through the corners, the far x and far y coordinates are at exactly the same point. Over here, it's a bit weird, but we have near x sort of in the negative direction here. Then we have near y, far x, and all the way down here, far y. And then we could do a similar thing for our blue vectors here, the ones that don't intersect. So this is the far y there. Near x is going to be somewhere back there. Far x is here, and near y is there. And we can notice something about these, which is that for our red vectors, the ones that do intersect, the near x coordinate is always less than the far y coordinate, no matter what. And you can see that this is not true for our non-intersecting vectors, where this bottom one here, near x, is greater than far y. But up here, it is sort of like this vector. I wish I had drawn this a bit better, but this top vector here, this near x, would be, over here. And so in this case, near x is actually less than far y. So this single single check is not quite enough to tell us whether or not a ray intersects, because just doing this would say, oh yeah, this blue one does intersect, when clearly it doesn't. So we have another relationship, which is that the near y is always less than the far x. And we can see that that is true for this one, obviously this one, and this one. Even though they're close, infinitely close, they are, that still does hold true until you get just up to the corner where they're the exact same point. And then we can see that this one does actually conform to that. This non-intersecting blue vector here does conform to that, where near y is less than far x. This one. But up here, now, this one is also marked as non-intersecting, because the near y here clearly is greater than this far x. And if it's not clear what I mean when I say greater, I mean further along the vector. That this is sort of like it has nothing to do with the actual like absolute coordinates. It's along the path of the vector. When I say further and near. So yeah, so to determine if a ray intersects with our non-rotated rectangle here, all we have to do is these two checks and then AND them together, and we've got our result. So that's the basic theory behind this. We're going to be sort of casting a ray or a vector from one rectangle at another rectangle, and if the rectangles intersect, then we will do something. We'll handle that collision in some way. Okay, so now let's do a little bit of housekeeping. Just going to add a couple more functions in our math library here. One to get the sign of a variable. So if it's 0, the sign is 0. Otherwise, if it's greater than 0, the sign is 1. Otherwise, it's negative, so the sign is -1. Okay. Then in our vec2, we'll add a couple new operations. One that just lets us compare both elements in our vector to a single value, so we don't have to like create a new vector every time we want to compare. And then down here, we'll have unit, which will use that sign function we just wrote. Just return a vector containing the sign of each of this vector's values. And then abs, which will return the absolute value of the vector. And then we can actually, just sort of for convenience, we can add a couple new operators here. So if I scroll up just a bit to all of our mathematical operators, these only work when our vector is the left-hand operand. Like this works if it's a vector plus something in that order. It doesn't work if it's something plus a vector. And that's kind of annoying in some cases. So we can actually define some operators outside of our class if we want our vector to also be able to be the right-hand operand. And this has some pretty intuitive syntax. So there's plus, and I'll just copy this for the others. Plus, minus, times, and divide. Okay, and then one last cool thing we can do, sort of in the same vein, is we can come down here and create another operator minus overload that takes no arguments, and this will just return the negation of this vector as a new vector. So just a bit more tricks to make these vectors operate more like integral types. Okay, that's all for our math library. We're going to do a bit in our graphics here. Sprite, we have this get width and get height, but it would be nice if we could just get those as a single vec2 all at once. Like that. And then we can use this in our dynamic class. Method called getCurrentDims, because remember our dynamics can have multiple sprites, but obviously only one like active sprite at a time. So we'll have a method to get the dimensions of our current sprite. Get current sprite dot get dims. And I probably need to, oh no, why not? Oh, for some reason this isn't marked as const. Huh, okay. Okay, so that's all the boring like housekeeping we needed to do. Now we can move on to our simple, just hacky example in our main file here. So I'll create a simple structure called rect, which has two vectors, a position and dimensions. I don't like that syntax. And we'll have a single method here that tests whether a given ray intersects a given rectangle. So a ray is just going to be an origin vector and a dimensions vector, or no, a direction vector, sorry. We have a single rectangle that we're testing for intersection with, and then we can have some pointers that we can actually write information about the intersection to. So we'll have the normal, so the vector normal to the surface that we collide with, if any. We'll have the actual XY coordinate of contact, and then the time, which refers to like the distance along the vector at which the intersection actually happens. Okay, so the first thing we need to do is calculate our near and far points. So we can do that by taking our rectangle's position, subtracting our ray's origin, which is just origin, and dividing by direction. And then to get far, very similar, we just have to add the dimensions of our rectangle. And I'm doing these as vec2, so this will calculate these values for x and y at the same time. Now, for certain weird, well, they're not that weird, but for cases where like your vectors are coming at this other angle from down here, these near and far values might actually be flipped, which is not an error. Like obviously this orange ray is still intersecting with us. It just means that we need to flip the values that are contained in these vectors. So if far.x is closer than near.x, we'll just swap the two. And then we'll just do the same thing for y values as well. Now we can do our simple checks right here to test if there is even an intersection. So if near.x is less than far.y and near.y is less than far.x, then there is an intersection. Otherwise, we'll just return false. There's no intersection. So at this point, we know there is one, so we can actually calculate like a valid time that it happens at. And this is just going to be the maximum of our two near times. So if we look at this, this is pretty easy to see. In this case, we have near y is much less than near x, but the first intersection actually happens at near x. This one, it's kind of hard to tell because they're the same, but here, it's the opposite of this bottom one, where near x is further back in time. The intersection actually happens at near y. But in both cases, it happens at one of the near variables. It's the one that's further along the vector. So that's why it's math.max of those two. Now, we have to do another check here, which is to sort of filter out these weird values, because this will calculate negative values, values that are backward in time, as well as values like this one here that are sort of not actually part of the ray. Like they are part of the direction of the ray, as in the ray will eventually hit that point, but with the magnitude of the direction vector that we've given, it won't hit that. And so we need to do a check to make sure that we're not looking back in time or too far forward in time. And the way we can do that is just if t is less than 0, so it happens like before this ray is at the origin, before the origin point, obviously we don't want that. But also if t is greater than 1, meaning the intersection happens at a point further along the ray than the direction vector we've given, then we'll return false. Because even though there is technically an intersection for a ray, like an infinitely long line essentially, that's not quite what we're interested in, because what we're doing, all of these calculations obviously are very dependent on time, on movement, and so we need to make sure that we're not accounting for collisions that will happen at some point infinitely far in the future. That doesn't make any sense. We're worried about the magnitude of the direction vector we've been given this frame. So if t is backwards in time or too far forwards in time, we'll just say there's no collision, even though technically there is. Now, if we've supplied a time pointer, we can write that value out. I've just supplied these as pointers. You could define like a struct that says like collision, like info or something, which we'll do eventually, that just contains all of this stuff. But for now, I'll just pass it in as pointers. Similarly, if we've given a contact pointer, we can write out the xy coordinate at which this intersection actually happens, which is very simple, just the origin of our ray plus the direction of our ray. I don't know why I keep doing ray dot. We have origin plus direction times t. Because remember, at this point, t is guaranteed to be a value between 0 and 1, so this won't be some like weird scaling. It will actually be some point along this like non-dashed vector here that we've given. And then the most important part, we need to give the contact normal. So the direction facing away from the rectangle that we've intersected with, because we need to know which direction that is if we want to actually resolve the collision. So this is like a very hacky solution. I'm sure there's some much better way to do this. Probably with like the dot product or something, but I just didn't spend a lot of time on that. As I said, I'm not as up to speed with linear algebra as I should be, so I just went with like a hacky programming approach. But I can still tell you like kind of what's going on here. And eventually this will get a bit better. So this is basically just shorthand for like a branching statement that says like it looks at which of the near values is greater and which of the far values is greater, and depending on that, it determines which face you're intersecting with. And that's all that is. And it's similarly to how I did the near and far thing up here as vectors. This just does that all in a simple like single calculation for both axes, for both x and y. So yeah, I'm not going to go into that too much. It's just like bad hacky math. But at this point, there is for sure an intersection. So we'll return true finally. Okay, so now we can actually test this in here. For simplicity, oh, I realized I didn't actually show you guys, because at the end of last lecture I was kind of rushing, so you didn't get to see maybe the result of all the work we did last time. If you played around with it, maybe, but I thought I'd just show it here, just to so I can explain a bit of it. I seem to have missed. Oh. Wow, I mangled this pretty bad, huh? There we go. Okay, so I just have a loop here that's like generating 100 dynamics and like a diagonal line, and then deleting some of them just to make sure that functionality works. And then within my map, I now have two large rectangles of stuff. One of them in the background, that's what this 0 is, it's on the 0th layer, and one of them in the foreground, which is this 1 there. So we can see the result of this. I have my diagonal line of all these dynamics here, and as expected, my player will appear in front of them, or on top of them, as long as they're further down the screen, i.e. closer to the camera. And you can see this here works for like any number of dynamics. I can weave in and out of them however I please. But then when I get up to this thing up here, this layer that is in the foreground, my player is always drawn in the background, along with the rest of the dynamics that are up there. So that's just the effect of that. And I suppose quickly I can show you. If you wanted to sort of reverse this calculation and make it so that further up the screen is closer to the camera, all you'd have to do is throw a 1 minus on that depth calculation, and then it works the opposite way. And similarly, if you wanted to do that for the x-axis, that would be exact same principle. You just pass in the center x value there instead of y. But I'll leave it at this because that makes the most sense to me. Okay, so that's what we have right now, but I'm actually just going to take this out for the time being, just to keep things as simple as possible. We will create a single rectangle, just call it box, and we'll put it at 0, 0, and its dimensions will be dsprite.getDims. So we'll just use the same sprite that we're using for our player there. And in our map file, I'll go ahead and make sure to actually set this correctly. So our chunk should be at 0, 0, and we'll just have a single tile, which is test2 at 0, 0. And we don't need layer or rigid yet. So now if I run, I should have just one thing at the origin. Yeah, so this is what we'll check our intersection against, just in this example here. So in our main loop here, we will first move our dynamic, and then before we draw, well, we're not going to move it. We're going to set its velocity equal to this stuff up here that we determined with the keyboard, just what we've been doing so far. But then in this dynamic list.draw function, that's where, well, this calls drawgroups.draw, of course. That's where our dynamic is actually updated. And if we look over here in our dynamic class, update is where the movement actually happens. Our current velocity vector is scaled and added to our position vector. So this is important. We're going to set our potential velocity if there are no intersections. Then we're going to calculate intersections if there are any and resolve them by changing this velocity vector. And then finally, we will actually apply the transformation. So we don't want to do this in the reverse order where we set velocity and then draw, and then after we've already performed this, then we scale the velocity, because that won't work. That won't do anything. Okay, so I'll have a vec2 origin, and this is going to start at our dynamics, our player's position, so the center of our player, and then the direction of this, as I sort of hinted at earlier, is how far into time we want to check for an intersection. So that's going to be, we want to check from our current position up to the intended final position for this frame. And we can see here very simply, the intended final position is just our current position plus our velocity scaled by the frame delta. So that's going to be our direction, is our velocity times render.get frame delta. Whoops. Our origin is that, and then we'll have our direction is that. I don't know why I define those in the same thing. Okay. Now we have, we'll set up some vectors to get the result of this collision check. So the normal and the contact point, we'll just set those to 0, and then the time. And now we'll actually check. So if array_rect on our origin and our direction, checking against our box up here, because we just have one object right now, and we'll send in pointers to normal, contact, and time. And these don't need to be pointers. These could be taken in by the function as references, but I prefer to, when I'm sending in values as parameters that will be modified by the function, I think it's a lot more clear to send them as pointers, because you have to supply them to the function in a different way, where obviously references, it's the same syntax for giving by copy, giving by const reference, giving by r value, l value, all this stuff. So it just makes it very clear that if I'm giving a pointer, this thing is going to change. Okay, then I have I'll just do an auto here. If there is actually an intersection, because this returns true if there was, then we now have some information about it in these three variables there, and we can scale our dynamics velocity so that the intersection never happens. So we'll get the surface normal times the absolute value of our velocity times 1 minus time. So again, there's a bit of hacky math there. I'm 100% certain there's a very clean way to do this with the dot product, but for some reason I just couldn't get it to work, so I just eventually gave up. But I'll show you like what's going on there. So I'll just take a simple case here of if we have our box there, and we're checking for intersection of some ray at our box, or I'll make this diagonal. So our surface normal here is going to be like that. And actually, I should have drawn this a bit differently. Let's say obviously we need that to be true, where our vector actually goes into the box. And so our surface normal is going to be that. Our contact point will be this. So this is just I'm sort of mapping this to the variables that we have here. We have normal, contact, and time. So green is normal, orange is contact, and then time is going to be this interval here, which is obviously a fraction of the total value or the total like distance that this vector goes. And so this value over here, the bit of our vector that went into the box that we are now trying to chop off, is going to be 1 minus time, because remember, time is sort of scaled so that time is 0 at our origin, and then time is 1 at the end of our vector for that frame. So this bit right here is the value returned as time, and then this, which we're interested in now, is 1 minus time. And the reason we're interested in this is because essentially we need to take our vector from this thing to this. And to do that, we need to chop off this extra bit there. So that's why we're interested in 1 minus time. And then we just go ahead and multiply everything by the normal. We sort of scale it so that it's moving in the correct direction away from the surface. And then this velocity, like these two things, there's some interaction there that should be linear algebra that is not, because I'm dumb. But this just like accounts for everything correctly no matter which direction you're coming from. That's what the abs does. Yeah, so that's the basic theory, is that 1 minus time just chops off the bit that goes inside of the rectangle that we don't want. And so when we add this to our velocity vector, the reason we add instead of subtract is that the value of our normal here, our surface normal in this case, will be -1 and 0. So that -1 actually does the subtraction for us when we add, because we're scaling everything by that normal. We just chop off the bit that we don't need and then reset our velocity to that. So now, if I run, I should get something kind of functional. So it kind of works. You can see it's a bit finicky. I can move into it quite a bit. And obviously the camera is a bit weird as well, because the camera is just tied to the keys, not the actual position of the thing. But yeah, so it kind of works, but not quite. So what's going on here? Let's come back to Paint. Just extend this a bit. Have our box here. We have our player rectangle. So there's sort of 3 things that are happening now every frame. First is we set our player's velocity. That's this statement here. Then we check for intersection. And if there is an intersection, we chop off the bit of velocity that was causing the intersection. And then finally, so that's what this bit is, set our velocity, update our velocity so there's no intersection, and then actually move our position according to that velocity. So that's the last step, is we actually perform the movement. And what that does is this. Because our ray is cast from the center of our dynamic, of our player. And so the center point is what is not allowed to collide with the rectangle. Nothing about like the actual dimensions of the box. It only accounts for the center point. And we can see that here, now that we know this. That's very obvious. Like our player is halfway inside of this box, no matter which direction we come at it from. And the solution to this is very easy because we have such a simple case. All we have to do is instead of checking for collision against this rectangle, we instead check for collision against like an artificially inflated rectangle that goes both like in both axes. It goes 1/2 more than the actual rectangle does. So width and height here being the width and height of our player. So we sort of scale this such that this intersection, this ray, will now, intersection here, will occur at this point of this artificial one, like that. And this bigger chunk is chopped off. And that will result in our player correctly colliding, like the actual bounding box of our player correctly colliding with this other thing. Because now this still looks a bit confusing, but now with this as the collision point, what's going to happen next frame is like that collision point is where my center point of my player moves to. Remember, all of our calculations are being done with center point. So when the center point is now out here, my player will correctly appear to not pass through the box at all, like that. And so to do that, all we have to do here, we have this very simple box. So we just need to center it in, well, its bottom left corner, instead of being at 0, 0, will now be at negative dsprite.getDims over 2. And then the actual dimensions of it, we will multiply by 2. And we can do this, just divide by 2 and multiply by 2, because they're using the same sprite. If this were a different sprite than our player, then this simple calculation would not work. But if we just run this here, we should get the result that we're expecting. There we go. So our player does not collide with the box at all. Obviously the camera's still a bit weird, but hopefully it's clear what's going on. And furthermore, something cool about the way we did our resolution is that player will actually, if I'm holding up and right here, my player will slide along the box. Because instead of just when we check for collision, we just set all of our velocity to 0, multiplying by this normal here ensures that only the direction of movement causing the intersection is taken out. Because we're adding this to velocity. So if moving in the x direction, like if we're colliding with the box from the left-hand side, then movement in the x direction is what's causing that. The y direction has no effect on that. And so we add to our velocity vector -1 in the x times this, but 0 in the y. And so the y value is not changed at all. So we can sort of slide along these surfaces, which is a lot nicer than if you just hit something, you just stop all movement. Like that doesn't really make sense. Okay, so now we have the same problem that we always have which is how do we scale this? And for something like this problem turns out to be incredibly complex and intricate. Because no longer, like for our dynamic stuff, which I would also say is quite complicated, the difficulty in scaling that is on the GPU. It's like, how do I batch this stuff together that is dynamic? I don't have any information about what it is. It has to be able to be added and removed at runtime in any order. How do I batch this together so that big chunks of it are drawn all at once on the GPU? That's a pretty tough problem. And we managed to solve it, and it was kind of hard. I sort of rushed through it, so we were able to do it in, like, I don't know, 3.5 hours. But that system took me weeks to figure out, like, initially. But we have a bit of a different problem with our hitboxes, which is that obviously no processing here is happening on the GPU, although I'm sure you could set that up. But for our cases, nothing's happening on the GPU, so that's not like the bottleneck. The bottleneck is sheer volume. Like, if we have 10,000 rigid objects in our world, and I don't know, even just a quarter of them are moving around, that's going to be 2,500 times 10,000 collision checks every frame. And that's just not going to work. Like, there's no way around it. It's not something you can, like, make clever use of the GPU to sort of enhance performance. It just doesn't work. Like, at a certain point, that n squared operation of checking everything against every other thing is too expensive. And we'll sort of see that here. I'll sort of walk through a simple example. We'll just generate a 100 by 100 grid of rigid tiles. And this is sort of similar to what we did with map data before we had our map stuff. I just went through this, like, stupid example just to show you that it's going to be slow and it's going to suck. So I'll write this here, and then I'll change our map data to reflect it. So we're all just going to be using the same sprite here just for convenience. So we'll have 10,000 rectangles. For each, we'll just calculate their width and, well, not their width and height, their X and Y position within our grid. And then, like, combine these into a vector just so we can do operations on them all at once. And then just have these calculations. These just perform, I maybe shouldn't have deleted that, but what we did up here with, like, getDims over 2 was the origin, and then getDims times 2 was the actual dimensions of it. This just does that for every tile, because now our thing is scaled by 2 automatically. And then we'll set boxes at I equal to pause and size. Okay, now in our loop here, we have a whole bunch of stuff that we need to check. So we'll go through each box in our list, check our player for intersection against each one, and resolve it. And then finally, we'll actually draw. And for this, at this point, our camera, like, not being lined up is going to be quite annoying. So I'll just, like, do a simple hack here to actually bind it to our dynamic, our player's position instead of just the keys. But obviously we'll have a more elegant solution for this. And then I'll also just draw the map afterwards. Okay. So now in our map, we'll just create a simple rectangle to represent this 100 by 100, so it's still centered at 0, 0, but now we have 100 tiles by 100 tiles. And let's run this, see what kind of performance we get. So we can see here, I don't collide with anything at all. And this is like a 10,000 things being checked each frame. And my frame rate is exactly the same as it was. It's like 1500. So I'm not sure exactly what is happening here, but somehow the compiler is like a wizard and is doing some crazy optimizations on all of this in release mode. I don't know exactly what or how it even figures that out, but what I think is happening is it somehow can tell that a lot of these will never be intersected with, because it sees that these values are never changing, and it says, okay, like you're never going to be able to get there. Something like that. I don't know. I don't even understand. But if we go to debug mode instead, the compiler will do less optimizations, and we should see a massive performance hit. Oh. Oops. So Visual Studio doesn't like me using sprintf, which I did have to use for Mac users. All you have to do is define the CRT secure no warnings. I thought I defined that, but I must have only done it for release mode. Okay, so now this is much closer to what we'd expect. We're getting, you know, like maybe up to 300 FPS for 10,000 things. And obviously that's slow. Like that is unacceptable. Our frame rate dropped by, you know, it's about 20% of what it was. And I'd like to point out that I've had to go to debug mode for this like dumb example. But again, those compiler optimizations only work because all of this stuff is hard coded. Our map pipeline, everything is dynamic. Everything is loaded at runtime. All of these values, the compiler knows nothing about them. It can't optimize anything away. And so for this stupid example, it is necessary to go down to debug mode to just see what would actually happen. But release mode or not, in our eventual system where everything is loaded in from a file at runtime, none of those optimizations would be possible. Just to prove that we do actually need a system for handling this well. So yeah, we need some way to well, actually another thing I'll say is that we've also performed optimizations here, like ourselves, because we know that our player is the only one moving. So we only have a single loop here, just checking our player against every other box. If all of these things were moving, that would be n squared. We would have to have like a for const rect and outer, you get it, and then compare every rect to every other rect, which that probably wouldn't even run. That would probably be like literally 1 FPS. So yeah, hopefully that, even though there's like weirdness with the compiler, hopefully that proves to you that this is slow. It needs optimization. So I've got a PowerPoint here about our solution. So this is global 2D collision detection and prevention. Again, this is only for non-rotating axis-aligned rectangles, moving at reasonable speeds. As we'll see in our implementation, the non-rotating axis-aligned part is kind of like up to the user. Obviously, that's what we're going to be doing for our stuff, but reasonable speeds is the most important, and I'll sort of touch on that as we get into this. So, the solution I've come up with to handle this, to handle the case where we have a world that has 10,000 different things in it, and we need to divide it up into, like, we need to somehow do some processing every frame to determine what rectangles we actually need to resolve collisions between. Because in that dumb example I gave there are 10,000 hitboxes, you know? But our player can't intersect with all of them in a single frame, obviously, because it moves at a reasonable speed, quite slowly. So we can only really, there's only even a chance for intersection against the hitboxes within its immediate area. And so we need some system for dividing up our space so that these relationships, these like groups of things that can potentially intersect on the current frame, are already grouped together, and we can only check collisions between the elements in each group. So what I came up with, kind of, is it's called a quad tree. It's a structure called a quad tree. All it is it's a basic tree structure, except every node has either 0 or 4 children, exactly. There's no in between. And in our case, because our game world is entirely 2D, just happens on a 2D plane, we can use this structure to represent our space, where each like sort of quadrant of space is represented by a node within our quad tree, and we can recursively subdivide that space into smaller and smaller quadrants just by adding on children to our quad tree. So I say I came up with this. The underlying structure, the quad tree, I did not come up with. This is something that is often mentioned when people, are talking about 2D collision resolution. But I do think I deserve a significant amount of credit because there's not really information about how to use it. All there really exists is it says, this is a quad tree, this is the theory behind it, this is how you could use it, and that's it. Like, common applications include 2D collision detection. Great. So all of the like implementation of this is mine, and because of that, it's definitely, it is not the most efficient solution, and may not even be representative of a typical solution. I have no idea. Again, I couldn't really find anything on like how this is actually done, because all games nowadays are 3D, so they use probably even more complex stuff. But the 3D analog of this would be an octree, where you take recursively smaller cubes of space and divide it into 8 smaller cubes, rather than just taking squares of space and dividing that into smaller and smaller squares. But so anyways, this is like not going to be perfect, but it's good. Like, it's fine. There are probably some bugs in it. There are probably weird cases that you can get that will like break it. And I just haven't had time to test all of those. So there are probably still issues with it. But mainly, it works for every case I've tested so far, and it's fast. It like, there is almost zero performance hit from this. It's like using it as like collision is not even being checked. It's crazy fast. So it's good enough for us, basically. So here is like a very basic quad tree. This is like a structure that we would never ever want ours to be in. Like, we wouldn't want this many partitions of space, just because this thing only contains 9 elements, so there's no need to group everything down this far. But for just showing like the structure of everything and visualizing it, this is very useful. So this sort of outer box here is like our entire game world. And then we have these 9 objects just sort of randomly distributed within our game world. And our quad tree has been divided up, recursively into more and more quadrants, to sort of partition these objects off into their own like local groups. And in this case, again, this is like a bad example. We'll see some better ones later about what ours will actually look like. But in this case, only C and B would be checked against for collision. A, it'll say, okay, A is moving, I need to check for collision. Let me check against all the things in my local group. Oh, there's nothing. I'm done. Super fast. Only B and C will undergo any checks. And we can see the actual underlying structure here, this shakily drawn tree. We have the root, which is again just sort of like this whole like big box, like the entire world. And then the order here is from left to from left to right on the tree, we have top left, top right, bottom left, bottom right. So we can see the top left quadrant contains only A, and then the top right is much more complicated. It has F in its top left, nothing in its top right, and then its bottom right is way divided. You can go through this. So I'm not going to go through the whole thing. You can just pause the video and figure it out if you want. But the most important thing to note is that for any node that is divided, any quadrant that has smaller quadrants within it, those nodes do not contain any of the actual elements in the quad tree. They only contain their child nodes. So you can see here, this top left quadrant isn't divided. It just has A, so it stores A right there. But this top right node of the root, again, the whole tree, like the tree spanning the whole world, this is clearly very divided. And so this node right here doesn't store any of these. Even though F, G, H, and I are contained within it, those aren't stored there. They're all stored at these separate places further down the tree. So that's the most important thing to know. And again, the basic principle behind this is to reduce the number of collision checks that are performed for any given object. And again, in this stupid case, only B and C will actually be checked. And so if you're interested in like what an actual one would look like, this would be it, sort of. Far less partitions, obviously, but stuff is still blocked off. So A and E are still separate, but B, C, and D are within their own space here, and then H, I, and J are in this one here. And as you add more and more things, this would divide further and further. So let's introduce like a moving player into our world and see how this interacts. So I've labeled some steps here, just for example, so we can see like at step 0, the player would only be checked against A. Obviously, we can see that it's moving in this direction, so there's no chance it'll collide with A. But the computer doesn't know that, so it just says, okay, I'll check against A. Very easy. We don't have to check against the rest of them. When you get here, it'll check against B, C, and D. E, nothing. H, I, G. Very simple. But this is a bit of an oversimplification because it doesn't show any of the effects that this player moving around will have on the underlying tree structure. So as our player moves, it divides the tree. It's like as it moves within the tree will dynamically resize and reshape itself to be more efficient as more and more objects are added to any given quadrant. So as a player moves into like these more populated quadrants, you can see nothing happens for this top left one or this bottom right one when there's only one other element. But with these that already have 3 elements in them, when the player moves in there, that quadrant will recursively subdivide itself. Now, this is like the fundamental sort of basis of why this works, why this is efficient, because it's completely dynamic. As stuff moves around, the quad tree will handle all of the resizing, all of the like other like stuff involved in grouping everything together into these efficient groups. And that's all you need, really. Like we don't have to do anything else. We just have to say, okay, I have this player, I have these other rigid objects, I'll put them in the tree, and then all I have to do in my game loop is say resolve all collisions, and the tree will figure it all out. So each thing here, each point is only checked against the points in its space, but we'll have to examine this a bit like more in depth later when we sort of have the heart-sinking realization that we're not dealing with points, we're dealing with arbitrarily sized rectangles. But we'll get to that when we get there. So this the reason I've drawn these lines as dashed is because they only exist for one single frame, the frame where the player is there. So when the player is at P0 here, this quadrant is just as it was. When the player is at P1, it subdivides according to these green lines. And then when the player leaves to P2, these green lines disappear, and it's just this regular big chunk once again. And the same goes for up here. Now, the reason it divides when the player enters it is I've used a threshold value, what I've called the threshold value, which is like the maximum number of elements that are allowed to be within a given quadrant before that quadrant subdivides. I've used a threshold value of 3 here. And this is a parameter that we'll be able to tweak in our actual implementation, just so that you can see, like, you can do some of your own benchmarking on it to see if certain values help for your certain distribution of hitboxes. But I think I'm just going to use 4 for mine. But in this example, the threshold value is 3. So when I have 3 elements, it's fine, but that's the maximum number. So when I gain a 4th, I now have to divide. And that division will take place recursively until none of the new quadrants contain more than the threshold value of elements. So what I was saying, though, is that when the player moves between these two quadrants, from step 1 to step 2, this subdivision only occurs when the player enters, and it like undoes itself when the player leaves. When the player enters, it's divided, and when the player leaves, it's merged. And this is because when the player leaves, the total number of elements contained within this quadrant, like all of the subquadrants that this quadrant has, the total number of elements in any of those subquadrants is below or at our threshold value again. Again, if our threshold value is 3, when our player enters, it's 4, so we have to divide. When our player leaves, it's 3 again. We now contain only 3 elements, and so we can merge everything back together. So, but why do we need to merge? Like, why should we even do that? Like, if our goal is to divide everything so that we're checking our objects against as few other objects as possible, why? Like, surely it would be best if our tree is subdivided as much as possible, just so that for any given point, the number of objects we're checking against is as small as it could be. And this is like a good thought. Like, that is absolutely the point of this, is to reduce the number of checks that happen. But that like assertion that should be the case, that we should just immediately divide everything as far as possible, is built on the assumption that, other than actually performing the collision checks, our quad tree is infinitely fast, which is not true. As you subdivide more and more, there is a significant amount of overhead in moving things within the tree. Not for this point implementation, but for our rectangle stuff, which we'll get to. And so what we want to do because of that, because there is this overhead, is that we want as few subdivisions as possible while still adhering to our threshold value. So we sort of have an upper-lower constraint model here, where we divide as much as possible just to the point where we have less than or equal to the threshold value in each subdivision. And further than that, we don't divide at all. So we sort of have to balance the time required for checking collisions with the time required for the just overhead of the tree operating, essentially. Okay, so as I've said, we missed a pretty huge factor in planning all of this out, which that our game world is not composed of points. Our game world is composed of rectangles. And this makes this previously clean, like, theoretical implementation of a quad tree, which unfortunately is, like, you can barely find much about this online, even this simple model. It makes this implementation very complicated and somewhat messy, but again, it still works. So here's a quad tree that contains 3 rectangles. When we add a 4th, we divide. So in this case, again, our threshold value is 3. So when we have 3 elements, we're fine. When we have more than 3, we have to divide. Now, this thing I've added it right in the center here, right in the center of the whole world. And D, if we're just going by our previous model of things in the tree are just single points, that like a single point determines their position in the tree. If we're going by that, then D would be just like the midpoint of D is down here in the bottom right quadrant. But we have an issue here, which is if A is moving this frame, and it's moving enough that it could potentially intersect with this top left corner of B, it will intersect with that, because D is only in this bottom right quadrant, A is in this top left quadrant, and so A won't be checked against anything, and it'll just pass right on through that until A is also in this bottom right quadrant. Clearly, that's an issue. So now that we have rectangles that actually take up space, we need to store them as part of every quadrant in the tree that they are a part of. So let's see what this would look like. In this case, D is in all 4 of our quadrants, so it's in all 4 of our nodes in the tree. A and B are just in the top left and top right, and then C is in both the bottom ones. So that's what this one would look like. So if we add another element, you can see we still have AD up here, but E now gets added to both of the right ones, the top right and the bottom right. Nothing else changes. We add yet another one. We now have to subdivide again, because for both of our right-hand quadrants here, we are at the threshold value. We have 3 C, D, and E in the bottom, and B, D, and E in the top. So we now have a 4th, and we have to recursively subdivide those. So our left-hand side doesn't change here. We still have A, D, and CD, but now we have B as part of this, like upper one here, and then DFE distributed. Again, I'm not gonna, you can pause the video and go through this if you want, but my point here is that our tree gets larger much faster than it did, because we're now storing essentially a bunch of copies of everything for every node that it's a part of. And as our tree subdivides further and further and we get smaller and smaller quadrants, this just, the amount of memory taken up by any given thing, depending on where it is in the tree, grows and grows. Now, I am highly suspicious that there's a way to do this that doesn't have side effects like this drastic. But I don't know. This is what I came up with. This is what we're doing, and it works. So to be clear, though, we aren't worried about the extra space, the actual physical amount of memory being taken up by having to store, extra copies of this stuff everywhere. It's just pointers, so it's not even that big. But even if it was that big, it's still not a big deal, because modern systems have so much memory, it doesn't matter. What we are worried about, though, is that as we divide more and more, what I was saying before is the amount of overhead required to move something within the tree increases, because we now have more quadrants, more nodes that we have to check against to see if something is contained within that node. And there's just more checks and more shuffling around of data, which takes time. That's the concern there, is time, not memory. But again, the system is so fast, even this somewhat inefficient implementation is overkill for us, so we're just going to run with it. Okay, so we can go over some of the basic components of this tree. So we have nodes, which are these quadrants, essentially, nodes within our tree. Each node represents a quadrant and stores either 0 children and some elements that are contained within that node, or 4 children and no elements. So that's what a node. And an element, obviously, is each rectangle within our tree. So they have 4 child nodes. They have a parent node, which is important. We'll need that to know how to merge stuff. They store a position of their bottom left corner and a single dimension value. Our quadrants are always going to be squares. As we'll see when we start implementing this, that's actually a requirement just to make this all work. They have to be square, and they have to be of a certain multiple of size. But yeah, so this position and dimension will just be used to check whether or not stuff is actually contained within that node. And then they have a list of elements. And again, the list of elements will only contain stuff if they have 0 active child nodes. But if they have 4 active child nodes, then the list of elements will be empty. Now we have the element. So this stores a position. For us, we'll just use the bottom left corner. It also stores a dimension vector. These don't have to be squares. These are just the arbitrary rectangles that are moving around in our world. They also have a velocity, importantly, and a list of nodes that contain it. So sort of similar to our dynamic system that we had before, that we did last time, where each dynamic like, what are they called? Each draw group stores references into the dynamic list that contains it. It's sort of this like interdependency that exists to make stuff fast. And we have the exact same model here where um, our element needs to know which nodes it's a part of so that it can quickly access those nodes and change them if it needs to. It also has a set of nodes that are the parents of nodes that contain it. Important, I used set there because if we look at a basic tree structure, I guess I'll just draw this. I should have included a diagram. But if we have a basic tree structure, I'll just draw one with like 2 levels here. So we have the root here, and we have just a basic world that's subdivided only once. So let's say we have this rectangle. This is in both of the right quadrants. And so our tree, like in memory, what this would look like, we'd have A here and A here, because it's part of both of these quadrants. Now, the parent of that, so A will store a reference to both this node and this node, but the parent of that is this node. And both of these have the same parent. And we don't want to reference the same, I call it grandparent twice. So a parent node of an element is the node that contains it, and then a grandparent node of an element is the parent of its parent node. And we don't want to store that grandparent node twice, so that's why it's a set. Just make sure there are no duplicates. And again, that's going to be for merging. So another important thing is that an element is like a proxy for something actually contained within a tree. It's not going to be like, we're not going to use our dynamics as elements in our quad tree. We're going to actually have another class, quad tree element, that our dynamics sort of interface with in order to handle collisions for it. And a reason for this, other than just extensibility and like making this clean so that you could sort of drag and drop it into any system, is that we have both dynamics and static geometry that have hitboxes. So we can't just store dynamics in our tree, because then that wouldn't account for the static geometry of our maps that are rigid. So that's why we do it this way. So now let's go through some of the operations on each of these types. So for node, obviously we need to be able to add to the tree, and that's going to be recursive. It's going to go through all of this node's children and all of their children, just figuring out all of the different nodes that the given element is a part of. We'll have delete element, which does the opposite. Then we'll have divide, which happens when the number of elements within this node reaches the threshold value. We will divide and sort of push those elements down to our children. We have the opposite of that, which is merge, where we extract all of our children from all the elements from our children, delete those children, and then now just store those elements ourselves. And like a sub method of this is get unique elements, which will just similarly to what I was saying, like how we have to store a set of the grandparents, many child nodes of a given node can contain the same element. So we need to check for unique elements. And that's a very simple calculation, again, because we're using pointers, so it's just an integer comparison, very fast. The element is a bit more heavy. It has some more functionality. So it has move, which will sort of take a new vectors from the host being the thing that like owns this element. This is what I was saying, like our dynamics will interface with this element class and pass all the work of handling collisions off to the element, and then when the element is done resolving collisions, the dynamic will copy the resulting values from the element. So it's sort of like a proxy. And move is going to be when we upload new values to our element from the host. So the host being a dynamic, we will give our dynamic's current position, dimensions, and velocity to our element. And given those, if anything could have changed, like if our dynamic's position has changed or it's gotten bigger, its dimensions, then we might need to move it within the tree. So we'll move it within the tree. That's what move does. And then update will actually check, it'll get a list or a set of all elements that are in the same groups as this element, and then check if there are collisions. If there are collisions, it'll resolve them. Then we'll have a couple methods here that are virtual. Intersects, which determines whether or not two elements intersect. Resolve collision, which is called to fix intersections. And again, these will be virtual, so making this as extensible as possible. You could take this and apply it to any type of geometry, but in our case, we're just doing simple rectangles. And then is contained by, which will be used by the node class to know if an element belongs in a given node. We have remove references to, which is like just some interdependency with the node class, remove from parents. Those two aren't very important. And then delete, which like this will happen when like a dynamic is deleted. It's like it's despawned, and so we no longer need its hitbox. We'll remove it from the tree completely. So we'll go through each of these in a bit of detail. And we're coming up to the end here. We have about 10 minutes, so I think I'll get through these slides. But then next time, I think what I'm planning to do is I'll sort of have these slides up as a reference as we're writing this, just so you can like see it and sort of remember the stuff. So for node.add, if an element is not contained by the node, according to its is contained by method, then we'll just return, because the element is not part of this node's, like the space that this node controls. We're not interested in it. It doesn't belong in this node. If this node already contains the threshold number of elements, so in our examples that I get here, 3. So if we're adding a fourth node, a fourth element to this node that already contains 3 elements, we will like preemptively divide it. If the node is divided, then we will just recursively call node.add on all of our children, and it'll perform all of the same stuff. If our node is not divided, so we've finally reached a child node which actually stores elements, then we will just add that element to this node. Next we have delete. So we'll just remove this element from this node's list of elements. This method does not have to be recursive, again, because once an element is added to the tree, it stores a list of the nodes that contain it. So when you delete an element, it can just go to those nodes directly and call delete element. There doesn't have to be any like is contained by checking or anything. But when we add a new element, we obviously don't know where it should belong in the tree, so we just end up adding it to the root, and that's why that has to be recursive. It'll like filter it down to the correct places. But for delete element, we just go to the node directly. And then most of the implementation for removing this will actually be in the element class, so we'll see that later. Node.divide, obviously a very important one. If our node size is less than or equal to the min size, which I'm not going to go into now, we'll define that. We'll see that when we actually start writing the code next time. Then it's an error. Essentially, it means that objects that are already intersecting have been added to our tree, which we don't have a way of handling. We only have a way of handling intersections that happen at runtime, and I'll talk about that more. So if this isn't true, so if we can actually divide, then we remove all elements from this node, because remember, each node stores either 0 children and a list of elements, or 4 children and 0 elements. So when we divide, we're moving from 0 children to 4 children, so we need to get rid of all of our elements. Then we create our 4 children, and for each child, we add each of our previous elements to the current child. And then we actually delete those this node's elements, this node's list of elements. Then the inverse of that, node.merge. If the node is not divided, we'll just return. I don't think that'll ever happen, but it's good to check. Then we will get a list, a set of our unique elements. So all of the unique elements contained by all of our children recursively. And if the number of unique children, if the number of unique elements contained by our children is greater than the threshold value, we still need to return, because that means that if we combine all of those elements into this node, then like we would have more elements than the threshold value, which is one of our constraints. We can't have that. Otherwise, if the number of unique elements in all of our children is less than or equal to our threshold value, we should combine. We should merge those children back into the current node. So for each element, we will erase this node from the current element's grandparents list, because these elements are contained by children of this node. And so that means this node will be a grandparent of those elements. We will erase this node's children from the current element's parents list. So that's just sort of like removing them from our children, essentially. And then for each of our children, we will delete our current children, the current child, and actually set it to null pointer, just in case. And then for each element that we now have in this set, we will just add them to the current node. So that's all of the node stuff. And again, like, don't worry about getting all this immediately. I'm just going through it so that you've seen it before, so that next time when we start actually writing the code, you'll have some foundation for all of this. So element.move, which again takes in the 3 host values from our dynamic, like the new position, new dimension, new velocity, as well as root, the root of the tree that we're adding to. If our stored position and our stored dimensions equal the new position and dimensions, we can just copy the new velocity and return. Because all of the like stuff for we'll just have to see this when we write it, but the velocity of an element has nothing to do with its position in the tree. Velocity controls its actual position, which does have to do with that, but basically it doesn't matter whether or not we're moving here. Just if our dynamic hasn't teleported, basically, or if it hasn't changed its state and it now has new dimensions, then we don't need to move it in the tree. It's in the exact same space. So we'll just copy the new velocity and return. Otherwise, we still have to copy like all of these 3 new values. We'll get a list of our original grandparents, so our grandparents at the current spot in the tree. We will remove from all of our parents and grandparents, and we will add back to the tree at the root node we've been given, and then we will remove all of our new grandparents at our new spot in the tree from our set of original grandparents. And then what this gives us is original grandparents now contains only those nodes that were grandparents in our old position, but not in our new position. So nodes that we were a part of, but now no longer are. And those might need to be merged now that we've moved out of it. So we'll just try to merge all of those. Element.update, this is the one that actually checks for collisions. If we're not moving, then we have no potential to cause collisions, so we'll just return. But then for each parent in our list of parents, we will get all of the elements in our current parent. And if the current element in the current parent is not ourselves, and we haven't checked this element yet, which is important because, each element can be in multiple nodes, so we don't want to check the same thing multiple times, so we'll store a list of what we've checked. So if we're not checking against ourselves and we haven't checked it yet, and if we intersect with this element, according to our virtual intersect method, then we will store a collision and some information about that collision. And once we've checked that, regardless of whether or not we actually intersect, we will say, okay, we've checked this, so we don't need to process it again. And then once we've gone through all that and determined all of the collisions, we will once again, we will check if we intersect with the current element. And then if we still do, we'll resolve the collision. And the reason we check for intersection again is, say we have 2 collisions. First one, we resolve, and that pushes us back to some space. And now that also happens to have resolved the second collision. So we shouldn't resolve that again, because that would give us, it's not only, it's not redundant, it's an error. It will do math that should not be done. It'll reduce their velocity more than should be, and so it would just have weird side effects. So for each collision, we have to check again if we intersect. Now we have this virtual elements intersect. For us, again, we're doing rectangles, so if a ray cast from the middle of this element in the direction of mvel, our velocity intersects the other element, we'll return true, otherwise we return false. And this is just the exact same thing we have in our main function right now. Then resolve collision, we just have this sort of hacky, terrible equation that I used because I don't know linear algebra well. And that just scales our velocity according to the direction we're coming at the object from. Is contained by is also very simple because we're just using non-rotated rectangles and we're checking if it's contained within a square, a non-rotated square that is a node in our quad tree. We'll just have a simple method for that. Remove references to, not important. Remove from parents, these are not important. They're just like helper methods for the node functionality. Delete is more important. So we'll copy our grandparents. This isn't actually what we're doing, obviously, but we'll sort of store our grandparents, remove from everything. So remove our references to every node in the tree. and then merge all of our grandparents. Because now not only have we moved, and so grandparents that were previously our grandparents may have merged. Now all of our grandparents are our previous grandparents because we've just taken ourselves out of the tree. So we need to try and merge everything. Okay, so we can now talk about a bit more about node.elements. I think I'll actually leave this till next time because this is the point at which we'll actually need to start like writing this code. So yeah, hopefully you enjoyed this. It was a bit more theory heavy, but I did. I hopefully this like stupid example in here kept it interesting for you. Just felt like we should actually do some amount of programming this time. But yeah, hopefully you are excited to actually get into this system. This is the most intricate thing we'll be designing. It'll probably take at least another 3 lectures, 2 if we're lucky. But yeah, I'm looking forward to seeing you in the next video.